Okay, is it running?
Yes.
Okay. Okay, so you calculated some model values for the distribution of protons after you had them interact with the gas in the galaxy. Okay, so we want to fit those model points to theory, well, to a theoretical expectation. But the problem is the model points don't actually have error bars, and neither does the theoretical expectation. Well, it has uncertainty. They might be large uncertainties, but you know. So how do you do that? Well, you use a process called least squares fitting. And basically what that does is it assumes, so like for instance, you're going to have, let's see, this is log of energy. And this is going to be log of number. So this is log plot. Okay, and you're going to have model points that look like that, or something like that. Okay, and you want to fit those points to a line. Because log plot, and you have a power law, and on a log plot, a power law becomes a line. Okay. But like I said, none of these have error bars. So least squares basically treats each and every one of these pretty much equally. Now, when you have real data with real error bars, so let me draw a picture like that. So log energy. And this is log something, but we won't actually write what log of it is. But if you had real data with like real error bars, for instance, what you would actually use, so this is, we're going to use least squares here. And this is, you would actually use chi-squared. And chi-squared is basically like least squared, except it gives you more weight to, it gives more weight to the points that have smaller error bars. But right now we're not fitting data, we're doing this one, so we use least squared. Okay, so how do we do that? All right, so we have, okay, so the distribution of protons should be a power law. And I'm going to call this n prime, because this is actually dn dv d log gamma, where, as you recall, this is the Lorentz factor, which is related to energy, is equal to gamma mc squared. Okay. Okay. Which I'm actually cheating and writing energy instead of gamma, but whatever. Oh God, I said that. Okay, so actually the form that we're looking at, so this is n naught, so that's a normalization. Or actually, it's a fiducial value. 1 minus pf. Okay. And what we're trying to find is this pf. Okay. So the first thing we're going to do is take the log of both sides. Now, this is, okay, basically what is left of the paper and pencil part of theory. Because most of even theory nowadays is done on computer code. So enjoy this while it lasts. Because this is basically what remains of the pencil and paper part. Okay. All right, so we're going to take the log of both sides. And the reason for doing that is because when you take the log of both sides, this power index here will actually come down. Okay. So let's go ahead and carry through this calculation. So this becomes log of n naught, oops, prime, plus some stuff, 1 minus pf. All right, and I'm going to just go ahead and do the log there. And then this becomes log e minus log e naught. Okay. All right. I I'm going to carry through this multiplication here. Log n naught prime plus log e plus log e naught minus pf times log e minus log e naught. Okay, because this is what we want. That's what we want. All right, this I'm going to put all this stuff together into a number, well, or a variable, which I'm going to creatively call b. All right. And since we're trying to fit a line, this is what we're trying to do. We're trying to find best fit PF value that satisfies an equation like this. Okay, I will define these things. Y prime is equal to log n prime. T prime is equal to log of e minus log e naught. And like I said, b prime is log n naught prime plus log e minus log e naught. Okay. Okay, so with least squares, okay, so you've got multiple points. So you'll actually have multiple versions of this. So I'm going to call these things, I'm going to label them J. Okay, and even the B, because you have E sub J. So all of these things will change for every point. Okay. Now, with the least squares, what you're trying to find is deviations between your measured values or your calculated values and this simple form, which is a line. Okay. So, and then you'll add them all together. Okay. So, let's sum over all the points. Minus PF TJ, let me write that a little closer, that TJ prime plus BJ prime. So this is basically just a line minus, or this is basically the, in principle, it would be the best fit line. Let's put it like that. Minus the calculated J values. Okay. So least squares. So this is the deviation, and you square it. Okay. Now, one more parentheses. Oh, is that right? Oh, that's later. Okay. So we want to find the least squares. Okay. So to do that, we want to actually minimize this, which means we take the derivative. Now, the thing that we're fitting for is this PF. So we take the derivative of this with respect to PF. So I'm going to put this in parentheses and write d by dPF. Okay. And since this is a minimization problem, we remember from freshman calculus or high school calculus, whenever you took it, that to find the minimum value of the derivative, or the minimum value of whatever's inside, you set the derivative equal to 0. Okay, and this is what we have to do. We have to solve this. Okay, do you want me to carry through this whole calculus?